Page 165, lesson 3.2 is on connecting representations of functions. Big parts of what we're going to be looking at in this section are going to be looking at something and telling if it's linear or nonlinear, and also once again looking to see if something is a function or not. So on 165, we'll go ahead and go through this, I guess. Eliza volunteers at a nearby aquarium where she tracks the migratory patterns of humpback whales from their feeding grounds to their breeding grounds. She recorded the distance in miles traveled by the whales each day for the first 7-day period of their migration. Based on Eliza's data, about how long will it take the humpback whales to travel the 3,100 miles to their breeding grounds? So if you look at the information here, we can see this for these 7 days, how far the whales went. So we could just add up these distances. If you add that up, is 205 miles. And then we could just figure up an average. So it was 205 miles. That was in 7 days. So if you do 205 divided by 7, it comes out to like 29.28571429. So we'll just say that's about 29 miles per day. And then if you look back in the problem, it says there's 3,100 miles that it's going all together. So 3,100 miles, basically 29 miles a day. So let's figure out how many 29s till we get to 3,100. And so that would be, it's like 106.89 something. So it's about 107 days. Okay, so almost a third of the year it's just traveling to the breeding grounds. So it's on the move quite a bit then, I guess. If it's then presumably going back to its other location, would probably take another 107 days about. So example 1 talks about representing linear functions with equations and graphs. So a 10,000 gallon swimming pool needs to be emptied. Exactly 2,000 gallons have already been pumped out of the pool and into the tanker. How can you determine how long it will take to pump all of the water into the tanker? So you can see from the picture here, they already told us 2,000 gallons have already been pumped in, and from the picture it tells us 720 gallons per hour are being pumped in. So with that information, we could come up with an equation for how much has been pumped into this thing. So we could say, you know, if we're doing our normal y and x, I guess, y would be like the amount that's pumped into this tanker. So the y is going to be equal to, well, it's 720 gallons per hour. So 720 times x, if x is the number of hours, plus 2,000. The 2,000 gallons have already been pumped. Okay, this would tell us how much there is. And the book is using a similar equation to this a little bit down further here to figure this out, because we're trying to figure out how long is it going to take to pump this out. And this one, going back to that equation we just had a second ago, The 2000 is like our y-intercept. That's our initial value. That's initially how much was already pumped into this tanker. And then the 720 times x, it's because it's that's how much is being pumped an hour. So that's a rate of change or slope. So this would be the equation then if we were going to solve this to figure out how long it would take to pump the water. And what we would do, just do the opposite operations like you've done. So they're adding, we could subtract 2,000. And then they're multiplying, so we could divide by 720. When you work this out and reduce it down, it's 11 1/9 hours. So it's going to take over 11 hours to pump this thing, and that's 720 gallons an hour. So it's going to take a while. It's a lot of water. If you look at this graph, they graphed this. Here's their y-intercept because 2,000 gallons were already pumped, and then 720 gallons each hour. That's the slope. So it's kind of rough stuff here because, you know, it's roughly graphing the points because we're going up 720 and over 1. Well, the over 1 is fine, but up 720, it's kind of an in-between point there. A little bit hard to tell exactly where to put that, but anyway. When you graph this, since it's got a constant rate of change, a constant slope, it is going to be a linear function. And linear function means it makes a straight line. The graph makes a straight line. In the word linear, you see the word line at the beginning. So easy way to remember, linear function makes a straight line. So if you look at the try it, as the pump is pumping water, the amount of water in the pool decreases at a constant rate. Complete the statements below, then graph the function. So this part we actually already did a little bit. So if there was 10,000 gallons and we've pumped 2,000 gallons already, if you subtract, that would be 8,000 gallons left in the pool. The amount of water pumped each hour is 720 gallons. And so the equation is really what we just already talked about. Oh, sorry, this is talking about the amount of water in the pool. Okay, so the amount of water in the pool is actually going to be going down. So we're losing 720 gallons per hour. But we did have 8,000 gallons to start with. And if that way doesn't make as much sense to you, you could switch it around and you could say we have 8,000 gallons and then we're losing 720 gallons per hour. Okay, just understand this way of writing the equation is not in the slope-intercept form like we've been doing. Slope-intercept form, you put the x term first, or in this case the h term, or we could make it an x term instead of an h term if you want. Anyway, this is what that would look like. And then they want us to graph this. So in order to graph this, we know we're starting with 8,000 gallons. Be nice if we just had an 8,000 here, but they're actually going halfway between 0 and 1,500 is 750. We're going by 750s here, so this is 8,250. So we're kind of in between those. Would be kind of our starting point. And what you can do is just take your equation, whichever equation you did, and you can substitute values in. So if t was 0, your y, or your number of gallons left in the pool, would be 8,000. If you put a 1 in place of the t after 1 hour, if you work that out, would be 7,280. Okay. If you look at the graph that they have, it's going over pretty far. So, maybe just out of curiosity, let's try 10. So if you try 10 hours, that would be 800 gallons left. Okay, so that's getting down there. 11 gallons then, well, and we already actually solved it in the last problem, right? We said it was 11 and 1/9 hours that it would be emptied out. So we actually know where that's going to go. So 1 is 7,280, wherever that is. Somewhere in here. After 10, it's at 800. And we know it's just a little after 11 that it's actually emptied. So that would be another point we could do. Another point we could graph. Okay, and then what should happen here is that these points should line up with each other. We're going to stay in the first quadrant because we can't have negative hours. I mean, I guess we could go back in time before we had the 2,000 gallons already pumped, but obviously we're not going to have negative water in the pool, so we're for sure not going to go past the 0 water being left in the pool point, which is the x-intercept we could talk about. Okay, and then the convince me says, how is the rate of change of this function different from that in example 1? So the difference is that on this one, so this is pretty specific answer here, I guess, but something like this would be a good explanation. The rate of change is negative in this problem because the amount of water in the pool is decreasing. In example 1, the rate of change was positive because the amount of water in the tanker was increasing. Okay, so we'll have another video that goes over the remainder of this lesson, but this gives you a start anyway on connecting representations of functions. Have a good day.